Okay, these are solutions to the energy problems from packet 6. Let's start. The diagram shows a block A having a mass of 2m and block B having a mass of m. They have different speeds, v and 2v, which the kinetic energy block A, the kinetic energy block B is, well, let's just do a quick kinetic energy, 1/2 mv squared. We're going to use variables. 1/2 times 2m times v squared equals, I should have put the square outside. 1/2 canceled with that, you get mv squared. 1/2 times m times 2v squared. So that's 2 is also squared, so you end up getting 2/4, so that's 2mv squared. So this is twice as much energy. So compared to block A, the kinetic block energy of block B is twice as great. If the direction of a car changes and its speed remains constant, which energy quantity must remain the same? It's going to be energy, right? Because momentum is a vector, displacement is a vector, velocity is a vector, kinetic energy is not. So it doesn't depend on direction. And if you just put in even 1/2 m v squared and you change the direction of v, you put a negative in there, it won't make a difference in the answer. What speed is this person running? If you get her kinetic energy and her mass, so 1/2 mv squared, 1/2 times 60 times v squared equals 1920. So let's solve for that. 1920 times 2 divided by 60 is v squared, so v squared is 64. So v is going to be the square root of that. V is going to be 8 meters per second. A boy is riding a bicycle with a speed of 8 meters a second. What's the combined energy of the boy and the bike? Again, this is to 1/2 mv squared, but there's two objects. So 1/2 times 45 times 8 meters per second squared plus 1/2 times 45, 1/2 times 15 times 8 meters per second squared. You could simplify it and you could simply say, hey, the total combined mass is 60. So you could also do 1/2 times 60 times 8 meters per second squared. 8 times 8 is 64. Divided by 2 is 32. So you end up getting 32 times 30. That should get you 960. What did I do wrong? Let's see. 64 times 60 divided by 2. 1920. Okay, I did something wrong the first time. 1920. The speed of a car is doubled, 1/2 mv squared. You double velocity, but that whole thing is squared, so it's an exponential relationship. So the KE is quadrupled. Answer A. Which graph represents the relationship between KE and the velocity of an object? Well, as I said, KE equals 1/2 mv squared, so it's proportional to v squared. So it should give us an exponential relationship looking something like that. KE versus v, like that, boom. You double velocity, quadruple kinetic energy. A rubber ball traveling east hits a wall, bounces back to the west. So when we did momentum, the east and the west were very important, right? Now it's asking about kinetic energy. So 1/2 times 1 is the mass, times 4 meters per second squared. 16 divided by 2 is 8 joules on the way. Afterwards, it's 1/2 times still 1 kilogram times 2 meters a second. Skip the units. Don't do that. So 2 squared is 4 divided by 2 is 2 joules. So it has 1/4 the energy, which makes sense. It's got half the speed, so it should have 1/4 the energy. Compared to the kinetic energy of the ball before it hits the wall, the kinetic energy of the ball after it hits the wall is 1/4 as great. Answer A. Okay, this looks like we're looking at some kind of energy. 1 kilogram book resting on the ground is moved 1 meter in various 1 meter relative to the horizon. Okay, so that's good to know. In what direction does the 1 meter displacement produce the greatest increase in the book's gravitational potential energy? So these lines all must represent displacement. This is worded a little strangely here, but gravitational potential energy is going to equal mgh, which basically just depends on the height, right? Doing this is going to increase the speed but not increase the height. So that increases kinetic energy. This does a little bit of both. This gets more of the potential, less kinetic, but this one is going to get the greatest potential energy because this is the one that has the most displacement above the ground. That gives you the biggest change in height. What is the GPE with respect to the surface of the water? You notice it gives you a starting point of a 75 kilogram diver 3 meters above the water. This is pretty easy. PE is equal to mgh, 75 kilograms times 9.8 meters per second squared. I'll put the units in there, you should know that. Times 3 meters above the water. Mass times g times h. So 75 times 3 is 750. It's going to be 3 times 750. So it should be around 2100, which would be probably answer B. I'm going to confirm that just with math. 75 times 9.8 times 3 gets us 2205. So 2.2 times 10 to the third joules, right there, answer B. An object weighing 15 newtons is lifted to the ground. So if it weighs 15 newtons, that means the force used to lift it is going to be 15 newtons. The increase in GPE is equal to, so the weight is 15 newtons, the force needed to lift it. So you could do work as force times distance, which should be 15 times 0.22, because that work increases the gravitational potential energy. You could do kinetic energy equals mgh, where mg is the weight, that's 15 newtons, times the height that you lifted 2.22, you get the same answer. So 15 times 0.22 equals a number definitely smaller than 15. Answer C, 3.3 joules. You can probably do a lot of this without a calculator. Okay, on to the next page. Which graph represents the relationship between GPE of a free-falling object and the object's height above the ground? So GPE is equal to mgh, and now you're comparing it to height. So PE is proportional to height, so it's going to be some kind of linear relationship. This is strangely worded because it's not with respect to time. Basically saying, because an object is going to start off pretty high. So, I mean, you're looking at this one, right? I mean, you might be debating between these two, but as it gets higher, it should have a more GPE. The strange thing you have to think about is that when you graph it, it's going to start high and then fall down. But that's not what this is showing us. We just need to make sure that you're not confused by time, because this does not have a time element in here. Okay. Two weightlifters raise identical masses above their heads compared to the work done. Was the work done by the other one? Okay. So work is going to be force times distance. In this case, you're lifting a 50 kilogram mass, but 50 kilograms times 9.8 is going to be 490 newtons. You don't actually need to do the math, but I'm just working this out for you. So they're doing 490 newtons times a distance, right? So one of them is lifting at 1.5 meters, and one of them is lifting at 2 meters. So one of them has 490 times 1.5, the other one has 490 times 2. So the one who's doing it, lifting at 2 meters, is clearly going to do more work. So let's see, compared to the work done by the weightlifter, the work done by the weightlifter is 2 meters tall, so 2 meters tall is going to be greater. A student does 60 joules of work pushing a box up a ramp that's 5 meters long. Okay, so in this case, if they're pushing it up the ramp, the work is just going to be force times the distance of the ramp. This will often throw people because you think you need to work vertically or something like this. That's not the case here, because they're saying that the force is being applied in the direction it's moving, which is up the ramp. So if the ramp is 5 meters and the force is up the ramp, then you get force times distance is equal to work. So force times distance, so 60 joules is equal to a force times the distance of 5 meters. Now it doesn't matter that the box is 3 kilograms or not, because the force is then 60 over 5, which should be 12. There we go. Okay. Constant speed, right? Let's see these words. You're pushing a crate. Most of the stuff is in the picture. Constant speed might be important. You're going from point A to point B. If the angle was increased, what would the effect of the magnitude of force F and the total work done on the crate as it moves from point A to point B? This is a bit odd. Oh, it's frictionless. Okay, that's important to know too. So the only thing that you are combating is gravity, and gravity is a vertical force. So as you increase the angle, you increase the vertical distance it needs to go. So if you had a steeper plane, then you would be going basically from here to here, right? So that the height would be here, as opposed to this time, the height is only here. So that would be like after height, and this would be initial height. So increasing it increases the distance it needs to travel vertically, so that should increase the work, because work is going to be force times distance. But in this case, it's just going to be weight times the height, mgh, or force times distance, because the only force you're dealing with is gravity. So let's see, the work would increase, but the force should remain the same. No. Well, the force is going to be contrary to mg sine theta, right? So the work would increase and the force would increase, because you're moving it the same distance in theory on this, but you got to use more force in order to do so. Flip over. I'm going to pause. The diagram shows points A, B, and C at or near the Earth's surface. As mass is moved from A to B, 100 joules of work are done against gravity. How much work is done against gravity as you move from A to C? Well, the important thing to notice is that they travel the same vertical distance. And work against gravity is all vertical distance, so it would be the object's weight if work is force times distance. It's going to be the weight, which is mg, times the distance traveled times 10 meters. But that's the same thing here. Mg times 10 meters. So it should be the same. So if it's 100 joules, then it's still 100 joules. A constant force, nice to always notice, of 1,900 newtons required to keep an automobile, blah, 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 moving at a constant speed. So there's obviously friction involved if you're using a force, but it's still going at a constant speed. The work done in moving the automobile a distance of blank. So it should just be force times distance, right? Force 1900 times distance of 2 times 10 to the third, which is 2,000 meters. So you can stick this in a calculator, 1900 times 2,000, and you get 38 with a lot of zeros, 3 times 10 to the 6th. So 3.8 times 10 to the 6th. Work, what unit combination? Well, work can be force times distance, so that could be a Newton times a meter. It could be 1/2 mg squared, because it's, or 1/2 mv squared, so it could be kilograms meters squared per second squared. So there's different ways to express it, but there's no kilogram meter squared, but there is a Newton meter, right? And that just comes from the equation, work is force times distance. Force is measured in newtons, distance is measured in meters. Okay. A force is used to push a cart a distance of 5 meters. The work done on the cart is really easy. Doesn't matter what the mass of the cart is. Boom. It just matters that the force is 20 newtons. And you're pushing it 5 meters, so that should be 100 joules. Student applies 20 Newton force to move a crate at a constant speed across a rough surface. How much work is done by the student on the crate in the first 6 seconds? So, let's see. 6 seconds. Well, the important thing is we know the speed, and it's a constant speed. That's good. Because if it's a constant speed, the distance is going to be velocity times time. T equals v I t. So velocity is 4 meters a second. Time is 6 seconds. So that gives you 24 meters. So you're using work is force times distance. So 20 newtons times 24 meters. So it should be 480 joules. Okay. A student runs up a staircase to a floor. We did this in class. That is 5 meters higher than her starting point in 7 seconds. Power. So power is work divided by time. Work is force times distance. So P equals, and you can even look at the reference table, see this at the very bottom. The work is the object's weight, which is mg. 40 kilograms times 9.8 meters per second squared. Force times distance. The distance they travel vertically is 5 meters. And since that's the work, and power is work divided by time, if the time is 7 seconds, let's put this all in our calculator. 40 kilograms times 9.8 meters per second squared times 5 meters divided by 7 seconds gets us 280 watts. W stands for watts. Okay. Relationship between work and the time of ascent. So work divided by time. What does the slope of this graph represent? Let's think about this. Work divided by time. I wonder where we've seen work divided by time. Well, let's look. Power is work divided by time. Make sure you're not getting confused with units and stuff like that. So if we know P equals W over T, W is represented by change in Y, T represents delta X, slope W over T is power. Notice how they have momentum there too. Momentum is a lowercase p. That is over here, different. They even put it in italics to somehow think it's less confusing. Raising an object vertically at a constant speed, then we have power. The weight of the object is. Okay, so this is where we get to these funny equations at the end. Power, we know power, but we know the speed, so we can actually probably look at this. Power is force times velocity. Now the force is going to be equal to the object's weight when you lift something. So in this case, if we just say P equals V over F, P equals F V, then F equals P over V, power over average velocity. But it's a constant speed, so the average is the same as the regular, and the weight is the force. 10 watts divided by 2 meters a second gets us a force of 5 newtons. Answer A. A 2,000 watt motor working at full capacity can lift a weight at a constant speed of, well, same equation here except we're solving for V. V is equal to P over F. So if it's 2,000 watts, remember power is measured in watts, divided by a force. Now it's a 400 Newton weight, so the weight is 400 newtons. So that's the force you're going to use. 2,000 divided by 4 should get you 5 meters per second. Okay. A boat requires a force to move it across the water at a certain speed. The engine produces energy at the rate of. So keep in mind, the rate at which energy is produced is going to be energy divided by time. Energy divided by time is the same as work divided by time, because work is the change in energy. So basically it's saying we're trying to find the power. And the power is going to be force times velocity. So if it needs a force of 600 newtons, just 6 times 10 to the second, and we know the velocity is 1.5 times 10 to the 1, so that's 15 meters a second. Turns out that the object's weight does not matter. So you have 600 times 15, should be 9,000, right? 9,000 is 9 times 10 to the third. Answer D. Okay. A student climbs the stairs, blah, 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 blah. What's the power of the input? We did this in class. Power is equal to work divided by time, but work is force times distance. So the force is 95 kilograms times 9.8 meters per second squared. It's the object's weight. The distance is 4 meters, and the time is 3 seconds. Force times distance divided by time. So you get 95. Let's see. 95 times 9.8 times 4 divided by 3. 1241. You'll notice they round. 1.2 times 10 to the third. Okay. You're raising an object in 5 seconds to what vertical distance? So it's basically the same equation. We're going to say P equals force times distance. Force is mg. The distance is mgd over time. So we want to find distance. So d is going to be equal to power times time over mg. So 120 watts times 5 seconds divided by mg, but in this case we know that object weighs 15 newtons, so mg is 15. 20. You need to know the difference between mass and weight, obviously, to get this easily. Divided by 15 should be 40 meters. Okay. A block is at rest on a frictionless horizontal surface. The block is moved 8 meters in 2 seconds by applying a force. What's the power? Power is force times distance over time. So force is 12 newtons times a distance of 8 meters divided by the time. There's something not right. Oh, 2 seconds. And the 3 kilograms doesn't matter. You notice that so many of these questions have information that does not matter. You got to sort through which is which. We got 48 watts. 500 Newton motor, a 500 watt motor lifts an object. Lifting, it means you're going to use a force equal to its weight. How much time does it take to lift it a distance of, so power is Fd over T, so T is Fd over P. Force, 100 newtons. Distance, 10 meters. Fd over P over power 500. So you end up getting, what, 100 times 10 is 1,000 divided by 500, so 2 seconds. Answer B. What's the maximum height you could lift an object in 4 seconds? So maximum height is just a distance, right? We got a power question again, so distance is equal to power times time over force. So 1200 watts is the power times the time of 4 seconds divided by 200 newtons is the force. So you end up getting 1200 divided by 200 is 6. 6 times 4 is 24. Answer D. A ball is thrown vertically upwards with an initial kinetic energy of 25 joules. How high will the ball raise? Okay, so you're basically turning KE into PE. So you start with 25 joules. So it tells you your kinetic energy, but the key to this is realizing that kinetic turns into potential. So if the kinetic energy is 25 joules, that turns into a potential energy of mgh. So we're setting 25 joules equal to mgh and solving for h. So h is equal to 25 joules over mg. The mass is 0.5 kilograms. G is 9.8 meters per second squared. So you end up getting, let's think about this. 25 divided by 50 should be around, no, 25 divided by 5 should be around 5. So I'm going to guess the answer is B, but if you want to put it into your calculator to be sure, 25 divided by 0.5, make sure you do this carefully. You don't want to accidentally divide by this and multiply by 9.8. Divided by 9.8 gets us 5.1. So B. We have a cart moving up a track. We need to figure out what the kinetic energy needs to be in order to reach the top. Well, again, this is a kinetic turning into potential. If they don't say frictionless, you can assume that it's probably friction. They say neglect energy loss due to friction. So kinetic energy becomes potential energy. So again, you need to figure out the kinetic energy and set it equal to the potential energy, equal to mgh. M, 5 kilograms, G, 9.8 meters per second squared, height, 10 meters. So it's funny, we're calculating kinetic energy by calculating potential. So you just do, it's going to be around 500, right? Probably 491, but if you're not sure, you can do 5 times 9.8 times 10. That should get you 490. If you got 490 and not 491, you probably use 9.81. Sometimes they round in different ways. They have 3 significant figures, so they're expecting that if you look at the reference table, I always use 9.8. They have 9.81 right here. Okay. A 1 kilogram block is the kinetic energy of the rock is approximately, okay. So again, they're asking you to find kinetic energy, but the reality is you need to do a potential energy thing, because PE becomes KE. So it's just like, hey, how much energy do you lose potential in terms of potential, because it becomes kinetic. So the change in potential energy, delta PE, and this is the equation they put on the reference table, delta PE equals mg delta H. I usually snip it off and don't use the deltas, or often do that, but let's just use the deltas because that's what we're looking for. And this would assume that there's no air resistance. They didn't explicitly say that, but let's say that. Mg delta H, so mass is 1 kilogram, equals 1 kilogram. G, 9.8 meters per second squared. And delta H, it falls 20 meters. So it's this much potential energy that it is lost, and that potential energy becomes kinetic energy. So you end up getting 9.8 times 20 times 1. So the 1 just goes away. 9.8 times 2 is 19.6. So it should be 196 joules, but they rounded. So if you got 196, you just got to round up to 200. If you put 9.81, you get a little closer to 200. Okay. A ball falls freely without friction towards the ground. Its total mechanical energy should remain the same. This is the idea of conservation of energy. This is why they say without friction. If you had friction, it would actually decrease a little bit because you would heat up the air and heat up the object as it fell. As a ball falls freely, it should speed up, right? So the kinetic energy should increase. What device transforms mechanical energy into electrical energy? Oh, we haven't gotten here, and we're not going to get here for a while. But the object that does mechanical energy is movement. So something that moves and creates electrical energy might be like a windmill. The air blows the windmill, and in the windmill blowing, it creates electrical energy. And basically, this is called a generator. So a generator generates electricity out of mechanical energy or movement. So a generator uses motion to create electrical energy. This is opposite than a motor. A motor actually uses electricity. You feed electricity into it, and it moves things like the axles of your tire. So a generator and motor are opposite sides of a coin. We'll see that later on. Generators generate electrical energy from mechanical. A motor uses electrical and creates mechanical. A student exerts a force on a rope to lift a crate. Compared to the work done by the student the gravitational potential energy gained by the crate is, it should be exactly the same unless it loses anything. So we need to think about this. How much, this is a tricky question, right? Because you want to say that it's the same, but let's see what we actually find. They use a force of 600 newtons, so the work done is 600 newtons times the distance of 3 meters, so that should be 1800. Now the change in potential energy, mg delta h, 50 kilograms times 9.8 times 3 meters. mg delta h, the delta h is the distance it travels, the work done is the actual force times the distance it travels. So times 9.8 times 3 equals 1470. So what we see is the change in potential energy is less than the work done. So it says compared to the work done by the student, the gravitational potential energy gained by the crate is probably 330 less. Now you might ask yourself why this is. Well, because you have a rotational element in here, some of that work is going to create friction in there. Some of that work actually creates a rotational energy as the pulley rotates. So you're not 100% efficient. You are adding energy to the system, and you're adding 1800 joules of energy, but it's not all becoming potential. Most of it is, but some of it's becoming something else, like rotational energy or internal energy. So not 100% conversion. Tricky question there. Okay. I'm going to pause this or stop. Okay, let's keep going on this. When a force moves an object over a rough horizontal surface at a constant velocity, so you're using a force, but it's moving at a constant velocity, that means that you have balance forces, which means whatever you're applying is going to equal and opposite the friction. So you get a forward and a backward force that are equal and opposite. That's your applied force and your frictional force. The work done against friction produces an increase in the object's internal energy. Friction creates heat, aka internal energy. A constant force is used to move a block sliding at a constant velocity along a rough track. Again, constant velocity, but a constant force. And that does not happen unless you have something opposing it like friction. So you're going to increase its internal energy. Now, you're applying it horizontally, right? So you're not elevating it, so there's no increase in gravitational potential energy. That's not going to happen. So you know it's not answers A or C. Now ask yourself, even though it's moving horizontally, is the kinetic energy increasing? Well, it's constant velocity. So if it's constant velocity, KE doesn't increase. It's only internal energy, so it's answer B. You pull a block to the top of an incline. 4 joules are needed to pull the block the full length of the incline. How much work is done against friction? Okay, this is one of those trickier ones. Let's think about this. How much energy do you actually do? So let's start with the change in gravitational potential energy, W delta PE, which is mg delta H. mg is 15 newtons, 0.2 meters. It doesn't matter that it's inclined if we look at that. 15 times is 3 newtons, right? Or 3 joules, sorry, 3 joules. So you've increased the energy by 3 joules. But you've done 4 joules of work. So, and you don't know the distance, but you know that whatever your force is, and it doesn't tell you what your force is, times the distance you travel along here, that's the amount of work. So you've done 4 joules of work, but you've only increased GPE by 3 joules. So that tells you something about the amount of work that you have done. It tells you that you've done more work than you've increased the energy. And if that's the case, that increase of energy's got to go someplace. And so that extra 1 joule, 4 minus 3, it's a 1 joule difference, has got to be work done against friction, heat. So that's a 1 joule. Okay. You raise a 72 Newton weight 5 meters. So delta PE is going to be 72 newtons times 5 meters, which is equal to 360 joules. Okay. How much work is done to overcome friction as the weight is raised? You'll notice 360 is one of the answers there. I can almost guarantee it's not going to be the correct answer. Because that's the amount that you've raised the potential energy. And the question is, how much work have you done? It says you've done 400 joules of work. So the work is the change in energy, delta E, is 400 joules. So you've done 400 joules of work, but only 360 of that has gone to potential energy. So 400 minus 360 is 40. 40 joules has got to be the extra work because the total energy that you've added has got to equal the work. So 360 plus something makes up that 400. 400 joules of work, 360 goes to elevating it, increasing potential energy. 40 joules increases friction. It doesn't say constant speed. That would probably be good to have in that problem, just to indicate that you're not adding kinetic energy as well. Okay, mass slides down an incline. There's a lot of detail in this picture. Here's the important thing we need to know. It gains 90 joules of kinetic energy while sliding. So let's see what the change in potential energy is. Delta PE is equal to mgh. It's 5 kilograms times 9.8 meters per second squared times 2 meters. The change, because that's all horizontal, mg delta h. 5 times 9.8 is around 50 times 2 is around 100. We'll actually get more exact. 5 times 9.8 times 2 gets us 980. I'm sorry, 98 joules. So it's lost 98 joules of potential energy, and a bunch of that has gone to kinetic, 90 joules of kinetic. However, that means that we've lost 8 joules we can't account for. So if you've lost 98 but only gained 90, there's got to be an extra 8 joules someplace. That's got to be friction. So that's an 8 joule difference in friction. When a mass is placed on a spring with a spring constant. Oh, we're getting into spring constants here. Cool. Okay. The spring is compressed. How much energy is stored in the spring? So if we look at this, we see PE sub S, potential energy for springs, is 1/2 kx squared. So 1/2 times the spring constant. They actually gives us that 30 newtons per meter. You could put the units in. It's compressed. X is the compression. So 0.5 squared, 1/2 kx squared. So let's think about that. 1/2 times 1/2 times 1/2 should be 1/8. So 30, you can put this in your calculator, times 0.5 times 0.5 squared should be 1/8 of 30. So 30 divided by 8 is going to be a little bit more than 3.75 joules. The spring in a scale stretches 0.025 meters, and you've got a watermelon. The spring constant is F. This is just a simple, hey, you've applied a force equal to the object's weight. F equals kx. You want to find k. So, and x is a compression or elongation. So, k is equal to F over x, which is 1 times 10 to the second is 100, divided by 0.025. So you know it's going to start with a 4, and it's going to be bigger than 100. So it's probably like 4,000. 100 divided by 0.025. 4,000. Answer B. Okay. It's unstretched, then it's stretched. 15 joules of energy are stored in it. What is the value of the spring constant? Okay, so this actually gets you probably a little, no, maybe not more information than you need. Okay, so x, right, is how much it's stretched. So it goes from 0.5 to 1, so x is the difference between those two. It's this, 1 divided minus 0.5. so x is 0.5. So if force, no, energy, right? Energy, KE, PE, PE equals 1/2 kx squared. We know 15 joules equals 1/2 times k, which is a spring constant, times x, 0.5 squared. Let's not forget the square. And we need to solve for k. So k is going to be 15 times 2 divided by 1/2 squared, which should actually be multiplied by 4. So 15 really times 8 should get you the same answer, 120. So 120 newtons per meter. Okay. A force causes a spring to stretch 0.2 meters. What's the potential energy? So this is a two-parter because it's telling you force and PE. So let's start with force. F equals kx. So 5 newtons equals k times 0.2 meters. So k is going to be 5 over 0.2, which is 5 times 5. So we get 25 newtons per meter. That's your spring constant. That is not the answer because we want to find potential energy. PE, it's a two-part question, is equal 1/2 kx squared. So 1/2 times k, 25 newtons per meter. And x, we know from this, is 0.2 squared. So 25 times 0.5, 1/2, is 12.5 times 0.2. Let's see, 2.5. Often it's a false answer if you forget to square this. So let's not forget to square that. So 0.5 joules, answer B. Elongation divided by force. Compared to the spring constant for spring A, the spring constant for spring B is, let's think about this. Elongation, x divided by f. That's the slope of those lines, right? We start with f equals kx. So k is equal to f over x. So interestingly enough, God, I hate questions like this. Okay, so the spring constant is equal to force over x. So sometimes when we do experiments, we'll graph it f versus x because the slope is more meaningful even if we reverse the dependent and independent variables. In this case, they probably graphed it, like you apply a different amount of force, you see what the elongation is. So they graphed it probably with the correct dependent-independent axes, but it makes the slope a little less meaningful or a little more confusing to us. So if k equals f over x, slope equals f over x, no, I'm sorry, k equals f over x, but the slope is x over f, that tells you that the slope is equal to the inverse of this, or 1 over k. So a big slope, if it's f versus x, right? A big slope would be a big spring constant. So big K, small spring constant for a smaller slope. So this is if we graphed f over x, right? Steeper line would be a bigger slope, which would be a bigger spring constant. This is exactly the opposite. So the one that has a big slope has a smaller spring constant. The one that has a smaller slope has a bigger spring constant. Pay attention to these axes. Every once in a blue moon, you'll see this on the Regents exam. Compared to the spring constant for spring A, the spring constant for spring B is, well, it's less sloped, but the slope is 1 over K. So even though it's less sloped, it should be a bigger spring constant. Okay. Which graph represents the elastic potential energy stored in a spring as a function of the elongation? PE equals 1/2 kx squared. Elongation is x. PE is proportional to x squared. Which one is an x squared function? It's exponential. It should be answer D. Elongation divided by force. So the spring constant of this is, why are these all? So F equals kx, right? So K equals F over X. Now, if you just pick a couple numbers and say, because not the best way to do it. Ideally, you'd find the slope, right? And the slope is X over F, so 1 over the slope is F over X. So you could say the slope is 0.5. You go up from here to here, 0.5. You go over 25. .02. So 1 over the slope should be your spring constant. 1 divided by 0.02. So 50 newtons per meter. But you could also just pick a value because it goes through 0, 0, which isn't actually true with a lot of springs. It doesn't quite go through 0, 0. But let's pretend. And you could say, hey, K equals F over X. What's the force? The force is 25 newtons. The elongation is 0.5 meters. 25 divided by 0.5 gets you 50. So there's multiple ways to do this. Because the slope goes through 0, 0, that'll work. But the best way really is to find the slope and take the inverse. Just be careful. A lot of the times you're not going to see it graphed on this way. Usually you'll see it force versus elongation. Okay. A spring has a spring constant of 120 newtons per meter. What's the PE stored in it as it's stretched to? So PE is 1/2 K, which is the spring constant, X squared, 0.2 squared. So 0.5 times 120 times 0.2, 12. You'll notice that's an answer. That's not the right answer. That would be leaving off the square. Times 0.2, so 2.4 joules. And with that, we are going to stop right now.